Hey everyone, and welcome to this explainer made by Forge College. I'm your host, and today we're picking up directly from our last module on quantifying scalability enhancement and module synthesis to solve, well, a pretty fascinating engineering mystery. You see, in our previous explainer, we talked about how reducing consensus delays makes the whole network run faster. But today, we're taking out our magnifying glasses. We need to figure out exactly how to measure proof of history's concrete contribution to that speed, rather than just kind of looking at the system's overall performance and guessing. So, here is our agenda for today's deep dive. First, the performance puzzle. Second, the distributed stopwatch. Third, the key performance metrics. Fourth, solving a performance mystery. And finally, number 5, the final verdict. All right, let's jump right into section 1, the performance puzzle, isolating proof of history. We all know the network has gotten incredibly fast recently. But, as engineers, we need to know exactly why. Which brings us to our central mystery. Who actually sped up the network? Is proof of history our absolute hero here? Or is it kind of like that guy in a group project who brings the snacks while someone else does all the actual research, but hey, everyone gets an A anyway? We really need to know what exactly is doing the heavy lifting. To do this, we have to totally shift our perspective. We're moving away from broad aggregate vanity metrics, like just looking at raw system-wide TPS, and we're moving toward a highly precise vocabulary. We want to isolate PoH's exact mechanical impact. Think of it like this. Aggregate performance tells us the car is going 200 miles per hour, sure, but isolated PoH impact tells us exactly how much of that speed comes from the timing belt versus the fuel injector. Moving on to section 2. The distributed stopwatch, a mental model. To investigate this puzzle properly, we need a solid way to visualize what PoH is actually doing under the hood. So picture proof of history as this massive mechanical stopwatch sitting right in the center of the network. Every single node can look up and read the time, but absolutely nobody can rewind it or tamper with it. Now, it's totally crucial to be realistic here. PoH is a brilliant timekeeper, for sure, but it doesn't magically give our data couriers super speed or extra strength. So, the main thing is to establish the strict boundaries of our prime suspect. Looking at this, you can see what PoH actually provides: monotonic ordering and relative intervals. Basically, it reduces the uncertainty of coordination. But it's equally important to see what it does not do. It doesn't physically push more data through your internet pipes, and it doesn't make signature verification cryptography run any faster on your CPU. It organizes the traffic, it doesn't build a wider highway. Because of those boundaries, we have to look at our stopwatch from 3 distinct measurement perspectives. I like to call this the rule of 3. First up, ordering. How many events actually stayed in the exact sequence they were submitted? Second, interval. How much time passed between adjacent ticks on our stopwatch across different replicas? And third, accuracy. How closely does this internal ticking match external real-world wall clocks?
Okay, section 3, the key performance metrics, cataloging the evidence.
Now that we have our stopwatch model, we really need to translate these abstract ideas into hard operational terms. This right here is our absolute blueprint. Look at how each metric maps directly to a distinct mechanism. For example, throughput might go up because leaders are scheduling faster. Confirmation latency drops when PoH reduces variance with deterministic ordering. Propagation delay shows us how quickly data hits peers, where PoH helps by providing an anchor so nodes don't have to waste time reordering data. Ordering fidelity is our most direct indicator. If events stay in sequence, PoH is doing its job. And timestamp drift? Well, if that's high, you likely have an external clock sync issue, not a PoH failure. But here is a massive pro tip for your metrics checklist. Focus on the tails. When you are analyzing this data, do not just look at the median average. You need to prioritize the 95th and 99th percentiles. Why? Because PoH's biggest victories are almost always found in reducing wild variance. It takes a chaotic, unpredictable network and makes it stable. Improving the worst-case scenario is what actually makes the network feel lightning fast to a real user. Let's look at this timeline and see how this builds into a near-linear chain of causality. To get our metrics, we essentially need to plant our flags at 3 exact moments. The millisecond a transaction is proposed, the millisecond it gets stamped with a PoH index by the leader, and the millisecond it is confirmed and written to the ledger by the peers. These 3 anchors will isolate exactly where the data is moving smoothly and where it's getting stuck. Which brings us to section 4, solving a performance mystery, a forensic case study. All right, enough theory. Let's apply our stopwatch to a real-world scene of the crime.
After a recent configuration change, we observed a massive 30% jump in throughput. The network went from 20,000 TPS to 26,000 TPS. The user community is obviously cheering, but as engineers, we have to ask, who gets the credit? Did proof of history do this, or was it something else entirely?
To avoid jumping to conclusions, we're going to walk through 4 mechanical steps of investigation. First, we define our anchors, those timestamps we just talked about. Second, we compute the stats for each link in the chain. Third, we run a sensitivity check to see what metrics logically should move if PoH were responsible. And fourth, we quantify our confidence using the data tails.
Let's break down our timeline into 3 specific durations, or intervals. D1 is the time from proposal to PoH index. This tests our leader queue. Basically, are the leaders dragging their feet? D2 is the time between PoH ticks. This tests the internal heartbeat of PoH itself. And D3 is the time from the PoH index to the final ledger write. This tests network propagation across the peers. We measure these before the 30% speed up and after.
And here is the aha moment of our data. When we look at the before and after, D1 stayed mostly the exact same. D2, the proof of history interval, remained totally steady, but look at D3. The 95th percentile propagation tail was slashed entirely in half, dropping from 120 milliseconds down to just 60 milliseconds.
So we can write our final forensic conclusion in our notebook. The propagation tail reduced dramatically, while PoH tick intervals remained stable. Therefore, PoH tick generation was likely not the primary throughput driver. The heavy lifting here was actually done by an improvement in systems like Turbine or Gulfstream, the network protocols responsible for physically moving the data. Proof of history provided the perfect ruler to measure the speedup, but it wasn't the engine that drove it.
Let's wrap this up with Section 5, the final verdict, rules for measurement.
As you're navigating your learning programs at PoH College, these precise distinctions are what separate good engineers from great ones. So here are your 3 core takeaways to annotate for your metrics checklist. First, always separate what PoH supplies, which is deterministic ordering, from what other systems supply, like raw network bandwidth. Second, rely on percentile dispersion and tails rather than just median averages. And third, always instrument your anchored timestamps, submit, index, and write, so you can decompose latency into its actual mechanical phases.
Knowing how to properly measure the stopwatch in real time leaves us with a pretty provocative thought. If we look backward, is this recorded history accurate enough for strict audits and forensic reconstruction? Well, we are going to tackle that exact question in our next explainer. Until then, I highly encourage you to visit forge.college to continue exploring this subject and dive deeper into our other Web3 topics. Thanks so much for watching, and keep building.